final design project presented 5 tasks to be executed by a machine. 1. Clear the surface of radioactive elements. 2. Collect rock samples. 3. Land spacecrafts in a marked safe zone. 4. Retrieve injured astronauts and their rovers. And 5. Place your country's flag. The 5 tasks will be executed during a 45-second time period.
These 5 tasks are incorporated in the House of Quality. The strongest relationships on the House of Quality are between the specific tasks and the kind of mechanisms needed to complete those tasks. One important negative correlation is between the requirement of fitting in the go-no-go box and reaching the center of the cylindrical cavity.
The prioritization matrix indicates that the available resources should be focused on the criteria in the following order: place the flag atop the mountain ridge, retrieve injured astronauts and rovers, collect rock samples for study, clear the radioactive elements, and lastly land the spacecraft in the marked zones. Construction throughout the class was based on this evaluation.
First design focuses on 3 tasks: pushing the radioactive elements out of the home zone, pulling the rock samples into the home zone, and retrieving the astronauts and rovers. This design utilizes an open base, a retractable arm, 2 extendable arms, and a scissor.
The second design completes the same 3 tasks of pushing the radioactive elements out of the home zone, pulling the rock samples into the home zone, and retrieving the astronauts and rovers through the use of scissor arms, motors, and machinery.
The third design attempts to collect rock samples, retrieve the astronauts and rovers, and remove the radioactive waste in the home zone. This design incorporates drawer sliders, a hook, cylindrical arms, and an open base.
The fourth design is based around a moving cart. This concept focuses on all tasks except for rock collection, utilizing a mobile system with extendable arms.
The fifth and final design completes all 5 tasks with consistent accuracy. This design incorporates trigger arms, a strap, a throwing ram, a swiveling subsystem, drawer sliders, extendable arms, and a ball releasing mechanism.
The most unique aspect about our design is the horizontal orientation. We decided to go with horizontal orientation because of our initial design for the rock collection, which we actually still have. This still in the same initial design. So I'm going to demonstrate that for you as step 1. So what happens is a solenoid back here pulls back, and a weight is resting on top of it that's attached to some strings, which connect to lever arms that drop these arms down. So I'll go ahead and show you that. The solenoid dropped, the weight came down, and the straps came out. Then a motor runs back here and winds up the straps and pulls the rocks all the way into the system.
After the rock collection, the second subsystem is fired by this valve, which releases the air from the tank into the 2 actuators here and here. The first actuator fires the tennis ball clearing mechanism, just like this. The second actuator is crucial because it allows us to maintain the horizontal orientation while still reaching the center mountain ridge. When it fires, the entire top system rotates and locks into place here.
The final step for our machine is reaching the mountain ridge system, and this is where most of the points are located. So we have an arm that fires, that deposits the flag into the cylindrical cavity, as well as collects the astronauts and rovers. The main issue we ran into while testing was the astronauts and rovers would fall through our arm, and then it would score points for our opponents. So we created this nice system that allows the astronauts and rovers to smoothly fall into our home zone. We also have these straps to prevent the astronauts and rovers from bouncing into our opponent's home zone. The third aspect of our mountain ridge subsystem deposits the spacecraft into the safe zones. This switch detects the safe versus unsafe zones, and then a motor pulls the gate up, releasing the squash balls into the safe zone. The mountain ridge subsystem requires a lot of accuracy, so we created some systems to allow for adjustability between the tracks. One of these things is removing the weight, which slightly drops the height of the front system. The other is adjusting the string, which allows for a change in the length when reaching the cylindrical cavity.
You ready? As long as it lays flat like the sides of the
Overall, the robot performed as expected. Our prediction showed an average score of 179.5 per round, which proved to be very accurate during the later rounds of the competition. Team Dare came into the competition seeded 18th and finished 5th in both the design and head-to-head competition. Our highest scoring round was round 3 when the team scored a total of 206 points, breaking the record for most points scored by any team throughout the entire competition. The design was an overall very effective machine. The flag and astronaut subsystems ran at 100% accuracy throughout the entire competition, while the rock collecting system ran perfectly for 5 out of the 6 rounds. The spacecraft and tennis ball system proved to be the least consistent due to variations on the track. Given the opportunity to make further adjustments, we would first focus on perfecting the spacecraft landings and adjust for a more accurate radioactive cooling system.
Cylindrical cavity. Reaching the center. That doesn't even make sense. It's when the deposit. Okay, wait. The system that